All right, we're about to dive into a bit of a digital detective story. We're on the hunt for a special kind of software bug, one that's so sneaky it can hide from even the most advanced tools. This is all about how you catch a ghost in the machine.
Yeah, this isn't your typical run-of-the-mill bug. We're talking about a true ghost in the machine, a flaw that only rears its head when a perfect storm of conditions line up just right, causes all sorts of chaos, and then, poof, it vanishes like it was never there.
So you gotta wonder, right? Why is it that some of these bugs feel like they have a mind of their own? It's almost as if they're lying in wait for that perfect moment to cause a problem, completely sidestepping all our attempts to track them down.
Well, this tricky culprit actually has a name. It's called a stateful bug, and it's as difficult as it sounds. See, it only shows up after a very specific, secret sequence of events. If you make one wrong move or do things out of order, the bug just stays hidden. It's not enough to send the right input, you have to send the right sequence of inputs. It's kind of like a secret handshake for making software fail.
So if these bugs are out there, why can't our usual bug hunting tools, our fuzzers, find them? Turns out they have a huge blind spot. They're fantastic at testing one action at a time, but they have a terrible memory. They just can't follow the sequence, the story, that actually leads to the bug.
This image here really gets to the heart of the problem. What you're looking at is basically a map, a state machine, for the HTTP2 protocol. Now, for some really well-documented software, a map like this exists. But here's the kicker. For most programs out there, there's no map at all. Testers are basically dropped into a giant unfamiliar city in the middle of the night, and they're just supposed to stumble upon one secret address by pure luck.
And this leads us right to the core issue. The old way of doing things, stateless fuzzing, is like a detective with amnesia. It tries one thing, gets a result, and then completely forgets what it just did. It can't connect the dots. What we really need is a stateful approach, a detective that remembers every single step of the investigation, learning the sequence and building a case to uncover the truth.
The big breakthrough came when a group of researchers realized that the map wasn't completely missing. The clues to build it were there the whole time, hidden in plain sight, right inside the program's code. It was a simple, clever clue that pretty much everyone had been overlooking.
These researchers started with a pretty ambitious goal. They figured they could automate this whole detective process. They didn't want to rely on people to manually go in and point out where the states are. Nope. They wanted to build a tool that could figure it all out on its own.
And here it is, the aha moment. They noticed a pattern in how developers write code. The names of the states, the very breadcrumbs they needed to build that missing map, were already there, hiding right out in the open inside a programming structure called an enum.
So what the heck is an enum? It's actually really simple. It's just a way for developers to give friendly, readable names to things. Instead of using confusing numbers like 0, 1, or 2 to represent what a program is doing, they can use clear words like idle or receiving underscore headers. And that's what makes it the perfect clue. It's literally the developer's own internal roadmap to the program's logic.
So armed with this amazing clue, the researchers could finally build a tool to automatically draw a map of all the software's secret pathways.
And let's meet the hero of our story, SGFUZZ. It stands for Stateful Greybox Fuzzer. The best way to think about it is as an automated map maker for software. It doesn't need a map to get started. It literally draws one in real time as it explores.
So how does this thing work its magic? Well, first, it automatically finds those enum state variables in the code. Second, while it's testing the program, it just watches how the values of those enums change, tracking the exact sequence. Third, it uses that information to build something called a state transition tree. That's our live updating map. And finally, this is the really cool part. It uses that map to intelligently guide its own testing, steering itself toward unexplored paths and secret rooms.
The result you get is just incredible. It's not a map of how the software is supposed to work based on some manual. No, it's a map of how it actually behaves in the real world, flaws and all. It's the software's true blueprint.
So, the big question. Did our automated detectives solve the case? Well, the results are, to be honest, staggering. Let's look at the evidence.
First up, this huge number. Compared to a standard fuzzer, SGFUZZ explored 33 times more unique state sequences. It wasn't just poking around the entrance, it was exploring deep, deep inside the software's logic.
And it wasn't just better than the baseline. As you can see here, it totally blew other state-of-the-art tools out of the water. It explored way more state paths than its competitors, putting it on a completely different level.
Because SGFUZZ had this map, it was also just incredibly efficient. It covered the same amount of code more than twice as fast. It wasn't wasting time just randomly bumping into walls. It could navigate directly to new and interesting areas that were hidden behind specific sequences.
Now, this is really why this all matters. All that smart exploration led to real discoveries. SGFU found brand new, serious vulnerabilities in software that's used all over the place. We're talking software that runs on millions of devices for things like streaming media and even exchanging medical data. And maybe the most important number of all? 8. 8 of these new bugs were so serious that they were assigned official CVE numbers. Now that's the universal standard for publicly known security vulnerabilities. This tool isn't just a cool idea, it's finding and helping to fix real-world security flaws.
So here's the bottom line. SGFUZZ found 12 new bugs, and 10 of them were the exact stateful kind we've been hunting. This research points to a staggering fact. For these types of programs, 4 out of every 5 bugs are stateful. Think about that. It means that without a state-aware technique, we're missing the vast majority of flaws. This approach isn't just an improvement, it's absolutely essential.
And that leaves us with a final big question to chew on. This entire breakthrough came from spotting a simple pattern that developers were already using. So if a simple clue like an enum can unlock so many of a program's hidden secrets, it really makes you wonder, what other clues are hiding in plain sight, just waiting for the right detective to come along?